Okay class, so now let's move to your AC equivalent. So why you need to do AC equivalent? Because you want to derive the gain. So the gain of your V out over Vs. So what is your gain? V out over Vs. So in order to do that, we need to change your circuit here, the original circuit, to what we call AC equivalent circuit. How are you going to change the original circuit to the AC equivalent circuit? So you need to do two things. The first one is capacitor need to be always shorted and your DC supply will be turned off. So means where is the DC supply here? We have VCC here. Turn off voltage source means shorted and then to ground. Okay, so now let's change the original circuit to the AC equivalent. So we have here Vs, the AC input. And here is Rs. What will happen to the capacitor? You will be shorted. And then you have here R2. And then here to your Re. And you have Rc. Okay, so your Rc here, since this is shorted, so now it will be shorted and then to ground. So you have Rc. Your Rc now is connecting to ground. Okay. But now where is R1 goes? So here you have R2. So now look at R1. See point A. R1 is connected to point A and to ground. So you can make your R1 and R2 is actually parallel. And the whole here will be grounded. Grounded. So now let's locate where is your output. Your output is at your collector and your input is at your base. Okay. So after you change this to AC equivalent circuit, so you need to change this BJT to the hybrid pi model. So we have three lines here. How you remember this one? Becha, right? So we have B, E, and C. In between here, we have R pi. In between C to E, you have a current source. Okay, recall back. In your hybrid pi model, you have two options. Either you are going to make your current source to become GMVBE like type 1, or you can make it like beta IB. So please take note, this is type 2, right? With your RE. So please use this one, beta IB. Can I use GMVBE? Yes, but the derivation will be quite different. Okay, so for this type, usually the question will give VA equal infinite. So means you know from the previous equation, your R0 is VA over ICQ, right? So when this is infinite, your R0 is also infinite. So your R0 will be open circuit. Open circuit. So now let's continue to the rest. So at your collector, you have here RC. And here we have V out. And then at your base, you will connect into your R2 parallel to R1. Here is RS. And then it connect to your Vs. And what will happen at your emitter? So at your emitter, you have what we call Re. So it's different from type 1. We have Re there. And then the whole here will be connected to ground. So this is what we call small signal equivalent of your common emitter with Re. Okay, now so let's start to derive the voltage gain. So AV equal V out over Vs. So where is your R in and where is your R out? So looking from here, we put your I here. So this is your R out. After your Rs is your R in. Okay, for your type 2, you will introduce one new parameter that is we call RIB. So here will be have RIB. Okay, so number 1, what you need to do, number 1 is we start at the output. So what is the formula for output? V out equal I out R out. So your V out here is a plus and minus. So the current will flow opposite direction to the dependent current source. So you are going to add here minus beta IB. This is I out. What is the output resistance? Looking from here, we have only RC multiplied by RC. So this will be equation number 1. Number 2, let's start at the input. So at your input, what is the input resistance? looking from here, what is your input resistance? So you have R2 parallel to R1 and also parallel to R pi. Okay, so number 3, you're going to find the relation between V out and Vs, right? So now let's move to your Vs. So at your Vs, we need to introduce another parameter here. Why? Because your Vs is not equivalent to this voltage drop here because you have Rs. So that's why you need to add here what we call V in plus minus. So V in plus and minus. So at your V in here, this voltage drop at your V in will not be the same with the voltage drop here. So what you need to do in the type 2, you need to have what we call a KVL equation across this loop because we have RE inside. So what is the KVL equation across the loop? Let's start with your V in here. So it become minus V in plus R pi. What is the current flowing through the R pi? So the current flowing here is what we call IB. IB plus RE. Now what is the voltage drop here is the RE. The current flowing here is IE equal to 0. Now look at the relation between IE and IB. As you know before, this is a AC, right? So all is small. IE equal IB plus IC. So we can take note IE equal actually 1 plus beta IB. Okay, so rearrange this equation so it become IB R pi plus RE 1 plus beta. So if you put your IB down, so it become V in over IB equal R pi plus RE 1 plus beta. Okay, so now what is actually V in over IB? So remember just now we introduced one new parameter. So now look at this point. So R is actually Ohm's law say R equal V over I. So if you want to find the resistance at the IB, what is the voltage drop across RIB? So we have here V in. What is the current flowing to the base? The current flowing to the base is IB. So if you equate this one to this equation, so you can denote the whole of this equation is actually your RIB. So what will be the equation of your RIB? RIB equal R pi plus RE 1 plus beta. So this is the equation for your input resistance seen from the base. Okay, so now you can denote your RIB is the long equation here, right? But there is some mistake here. So this is, we need to recall back for R in. So your R in is actually R1 parallel to R2. It's not parallel to R pi. Sorry for that. So it's actually parallel to what we call RIB. Okay, so you can denote here your R in is actually R1 parallel to R2 parallel to not R pi but parallel to RIB. Why you didn't denote R pi? Because we have RE here. So we need to have the summation of the resistance here. That is what we call RIB. Okay, so we're not finished yet. We need to derive your VS. So now look at your VS. What is the relation between VS and V in? So let's draw the voltage divider again. Here is VS. Here is your RS. Okay, the whole here is what is the resistance at the whole circuit here is actually your R in. What is the voltage drop here is your V in. Now how you can find your V in? V in equal R in divided by R in plus RS multiplied by VS. And then you can get 1 over VS equal 1 over V in R in divided by R in plus RS. This will be equation number 2. Okay, so now in the previous derivation, you already got your V out. So now you can get the relation of your PS. So you can summarize here how you can get the gain. So your AV equal V out over Vs. V out over Vs equal V out multiplied by 1 over Vs. So how you can get your V out? So your V out is from equation here, from your output is actually equal minus beta IBRC. How you can get 1 over Vs is actually 1 over V in from this equation, R in divided by R in plus Rs. Okay, so now you have here IB, but here you have V in, right? V in. So remember just now the RIEB equation, you have this long equation, V in equal IB R pi plus RE 1 plus beta. Substitute that inside this equation, so it becomes minus beta IB RC. Since it is 1 over V in, so it become 1 over the whole equation. So it become I, just now is what? IB. So become IB R pi plus RE plus 1 plus beta. So you have here R pi plus RE 1 plus beta. So means this whole here is actually your V in. Is actually your V in. So just multiply by R in divided by R in plus Rs. So now what you need to do now, you can cancel your IB. So from there, you can calculate your AV. The gain is actually minus beta RC divided by R pi plus RE 1 plus beta RE divided by R in plus Rs. So the equation is derived. So this is as shown in the slide. So the step is the same. So when you derive, you can get this equation, the long equation, minus beta RC divided by R pi plus 1 plus beta RE. And then you are done with the derivation. So we will move to the example in the next video. So if you have any question, do let me know. Okay, thank you.